paper that was on looking at networks again from a different point of view. It's trying to see the process by which delays spread through a public transport system and then finding exactly where the delay started. So source estimation for propagation processes of complex networks. Juliane.
Thanks a lot. Thanks a lot for the invitation and accepting the paper. I'm really happy, and I'm very happy to be here. Thanks for organizing this very nice family-style workshop. It's actually a chance to get to know people. So as you said, I'm speaking about source detection and source estimation of propagation processes on complex networks. And this time, I apply that to the propagation of train delays. So transportation networks. I think we didn't have transportation networks yet. So this work is in collaboration with my colleagues from the Applied Math Department in Göttingen, where I used to be. Now I'm in Boston, but most of the work was done in Göttingen, so that's why we have this funny combination of affiliations here. So the idea is not, as usual, to actually do a prediction of a process, what it might look like in the future. But for that, we also need to know where it actually started off. So the idea is to trace it back and to figure out where it comes from. Where did the spreading start? We assume a very simple databases, which is just a network graph with denoted with nodes k, linked by links L. And we only have a snapshot of a spreading pattern. And this spreading pattern is observed in the following, so that we have observations at each network node k at a time t. We do denote it to be time dependent here, but actually we just look at one particular time point. So any time during the spreading process, we take out one picture and we try, based on this, to find the origin. We have two methods here. First is the effective distance median, and the second one, the recursive backtracking. How this paper developed, there's usually some kind of small history behind the paper, how it developed. So this one actually started with the E. coli outbreak in Germany about 5 years ago. So there was a time when people in Germany didn't eat lettuce, didn't eat cucumbers, didn't eat tomatoes. And well, usually foodborne disease outbreaks in industrialized countries are not that severe. So the question here was, can we actually find the origin where this contaminated food was produced based on a spreading pattern? So we were pretty successful with using the effective distance in that context, and then we were wondering, does that actually work for general spreading processes, or is that specifically for infectious disease? So that's why we thought, well, the railway networks are well-defined. Delays on railway networks can spread according to very different propagation mechanisms. It's a quite different application, but on the other hand, there are a lot of similarities. So end of the story will be, well, infectious disease are kind of a little bit similar to delays in train networks. So looking at an example for delay spreading, we do have some data examples from the major German railway operator, Deutsche Bahn. And we can see a network with about 1,000 nodes, about 3,500 links in between them, a rather low density, so it's a very sparse network, which is super typical for transportation networks. The average degree is relatively high. Diameter for having so many stations is only 11, so it's a kind of very efficient network. And we have a rather large transitivity in comparison to other transportation networks. And that is due to the reason that we have not only high-speed network here, but also regional train connections. So I have to say each node represents a station in Germany, and these nodes are linked if there's a train in between, running between them. So if you can go directly from one station to the other, let's say you have a direct connection from Berlin main station to Potsdam, a city close by, or you also have a direct connection between Frankfurt and Berlin, so you move those nodes closer than you actually would think of. So the delay data, we have about 6,000 individual trains where we observed whether they are delayed or not and how much they are delayed. But these observations are only from about 300 stations. So with that, we actually have like a sub-network only having the high-speed, long-distance trains in here. Okay. So in general, in 1 year, the observation period was in 2012 to 2013. We have statistics which says that about 20% of the trains are delayed more than 5 minutes, which doesn't sound that bad, but the one thing is, it's a huge topic. If you want to fight with a German, speak with them about train delays. It's a huge thing. So, but it's not only the inconvenience for the people, it's also an economic burden for the operator. So, in the example here, we have a major failure very early in the morning, which spreads through the system over the day and kind of remains in the system over the day. So in that example, we have about 30% of trains being delayed, 1/3 of trains being delayed, 32%. And we can see that some of the trains have some really major delays, so you essentially don't arrive. Why do train delays actually spread? So there are two major reasons. First reason would be, I'm sitting in a delayed train and I have this connection I actually wanted to take, and you ask the conductor, could you ask the conductor whether the other train could wait for me? So with that, the train you're in, which is delayed, is going to transmit the delay to the other train. First option. The other thing is the track occupation. That is only valid for railway networks because it's very difficult to pass one train the other. So here you have the difficulty in comparison. Like if you take a bus or something, if one bus can pass the other, but on a railway you're like you cannot just jump out and derail and jump on the track again, so it doesn't work. So these are the two major reasons. There are a bunch of others, but we focus on these. Questions in transportation science we would like to answer, or people in the applied area are really interested in, is the first one, which sounds super obvious, to distinguish between source delays and propagated delays. But since the data is usually not very precise, that can be a real issue. When you found which one is a source delay, you might be able to determine what is the cause for the delay and who is responsible. So who is paying for the reimbursement for the passengers who are too late. And maybe you're also interested in just eliminate the cost. So if you have something in your system, you want to eliminate it. And in the long term, if you cannot eliminate the cost, you may want to construct something which is called a robust timetable. Means a timetable, adapt your timetable so that the delays are considered and you actually have like longer passenger transfers or anything like that, right? Okay. So that was a brief motivation. The outline of my talk is that I first speak about the source detection methods, then I'm going to the results, and then I conclude it. So starting with the source detection methods, first a short literature review, because that area has been very active during the last years, and it's sometimes a little bit difficult to keep track. Then I'm introducing the effective distance median and the recursive backtracking methods. So, very popular, the whole idea of we are interested in actually finding the origin of a spreading process started not that long ago, like about 6 years ago. One very simple work is by Comine and Daventura, which is essentially just maximizing a degree normalized betweenness on the transmission tree. So that assumes you know the transmission tree, you don't really need the rest of the network, and then you look for the most central node. And they found degree normalized betweenness to be the best predictor. A very popular one is the rumor center, which maximizes, now listen, the permitted permutation of the infection sequences, which essentially breaks down on a tree to a closeness centrality. Another one is the Jordan centrality, and that minimizes also some type of centrality, node eccentricity. we base the effective distance median on a effective distance source detection that replaces the ordinary shortest path distance, as everyone knows it, by a effective distance, be surprised, and then optimizes the radial symmetry. So that's what we also used for the foodborne disease outbreak. And for the train delays, we generalized that and used that. If you're interested in that area, I definitely recommend that review here. There are a bunch of methods, and they're doing some simulation studies. It gives you a good overview of what is happening there. So, motivating the effective distance, since we based the effective distance median on it. On the right hand, you see a simulation on the World Airline Network. And that's a typically complex pattern. So there's an epidemic which starts over here in Cyprus in the eastern Mediterranean. Wait a second. Yes. So it goes to the Middle East. Cyprus is traditionally connected to England, goes to Europe, the rest of the world essentially. Typically complex pattern. You can reorganize that efficiently by just putting the origin here into the middle of the shortest path tree by using the effective distance, and then you observe a circular pattern. Now we have to wait a minute. You observe here a circular pattern which you could already observe in Middle Age epidemics. So we use that reorganization to actually project our complex pattern here onto a more organized pattern which is easier to understand. A formula that looks like this. So when I did my PhD in Göttingen, every now and then I wanted to go home to Berlin, so I was looking for the shortest route I could take there. So one thing would be the gray route, which I could take, so which is pretty much just going straight, traditional way. Problem here is over here there's a mountain range. And you're probably aware of the German Autobahn, the highway, which is much better because you essentially don't have speed limits in that area you have. So using the motorway, it's much easier to go up and then further east, and this is essentially shorter considering the costs or the speed limit. The effective distance works very similar. You just don't, you have a more complex thing of defining the costs, which combine the topological distance in terms of the number of segments you have to pass with some type of path probability. So this is just the product of the transition probabilities going from one node to the other. Based on this, we generalized the effective distance or source detection method we used, which was originally introduced by Borgman and Helbring, and define the origin as the minimization of some expected of some expectation here, and it's the expectation of the effective distance from the considered source candidate K0 to all the other nodes in the network. It turned out, after speaking with the people from the applied math department, that this is actually a network median as it is defined in location theory. So that is already a concept. It gives us the advantage that we do not have to consider the variance of the spreading process, which which tends to be a very unstable estimation. So that's why we reduce that only to the expectation here. So we estimate the expectation by simply having a weighted sum of the distance from the source candidate K0 to all the other nodes in the network, weighted by the relative delay magnitude in those nodes. Okay, so looking at the second method, this one is constructed a little differently, and it's specifically designed for train delays. So here we follow recursively the path of each delay along the network. So we kind of trace delay along the network links. So that's explicitly making use of the way how delays spread in a public transportation network. And I have to say from the beginning, it's a great method which works for public transportation and it works amazingly for public transportation, but it actually really considers the way it spreads. So we require for that the source is constantly introducing delays into the network, so that we can follow them, and it's not like introducing something and stopping, because then is where the method actually breaks down. The traditional ideas of recursive backtracking, they're a bunch around, but we have much less precise data. So we have to simplify the algorithms which are around, and that's what we were thinking of. So we have an observation of delays at each network node over the time, and then we define just a counting variable which counts the advance. So we consider just any node which has a delay larger than 0 in the network. As an example, that could be that guy. And then we look for the adjacent node, which is basically here the decision between this and that guy, which has the maximum relative delay. So we consider this one, compare that with the delay over here, and decide, okay, that one is larger, so we jump there. Then we do that again, look for the one which has a larger relative delay, jump there. And so on, until we end up at a node where we realize, okay, that relative delay is larger than any other node which is adjacent, so we consider that one to be the result of this iteration and increase the counting variable for node number 4 in that case. So we do that for all nodes which are experiencing n delay, and by the end we rank all nodes by this count variable bk. Okay, so having the two methods introduced, we want to see how they do. First, a simulation study, an application, and some idea for an uncertainty assessment. The simulation study was a big playground for us because we have a well-defined network, and delays can be propagated in really a lot of different ways. So here we have an artificial network which is similar to the high-speed network in Germany, which has like a 320 nodes, 450 links. The density is still low, average degree much lower, so much more similar to other public transportation networks reported in literature. The diameter is 25, and we have a rather relatively large transitivity of 14%. The playground was actually Linton, which is a simulation software which has implemented different optimization techniques of how you prioritize passengers transfers and track occupation if you change the order of the train or not. And we assume that we have a line plan and a timetable, so that's what we put in as a basis. And then each scenario consists of 319 simulations, which refers that each node in the network once is a source node of spreading delays. So for this source node, we generate 30 source delays with a magnitude between 1 minute and 15 minutes. And then we do the delay propagation through the network, essentially 4 hours, applying these different propagation mechanisms we assume. And then we have these observations for these 4 hours, and we take 10 observations from that. So we have 10 sequential pictures of relative delay for each station at this time 1 to 10. That's the basic setting. For the general comparison of the estimation methods, we assumed a very practical rule by thumb propagation mechanism, which essentially assumes, okay, a train waits a fixed amount of time for a passenger transfer or it leaves. So if the delay is more than, let's say, 5 minutes, the train would leave. If the delay is less than 5 minutes, the train waits and the delay is propagated. Yes. So in the graphs we can see the observation time on the x-axis, and in the left hand we see the probability of correct detection. And we have the different methods in comparison. The pink one is the recursive backtracking, and that can be seen since it is specifically designed for train delays as an upper boundary. And we can see that the effective distance median using the relative delay magnitude, which is like the yellow curve, is not doing that bad in comparison. It's a little bit lower, but it's also more general. If we only consider the counts of delayed trains, so we do not consider like the delay magnitude, the delay minutes specifically, we do a little bit worse because we're essentially throwing information away, but we might not have it. And as in comparison, both methods outperform by far the centrality-based method, which is optimizing the degree normalized in-betweenness. Looking at the rank of correct detection, we have the observation time on the x-axis, the rank of correct detection on the y-axis. We can see that the centrality method is even having a large variation, specifically in the beginning. The other methods are doing kind of the same relatively to each other. I have to explain that rank of correct detection essentially means which rank the correct source will be ranked. That was a weird sentence, I'm sorry for that. Means a rank of 1 is a correct detection, and this would go as into the probability. So we also had a look at the distance to the correct detection because particularly the people from the German railway operator were interested in that because it's a more practical thing to look at. We look here in kilometer on the y-axis. So it goes from 0 to 150 kilometers, which is essentially like 1/4, 1/3 of Germany. And we can see that, especially interestingly, that recursive backtracking has a rather large variation in the beginning. So we might have a large correct detection here, but if we don't correctly detect it, we end up in a totally different area of Germany. The other methods, so that goes down, and then we are as good as the effective distance median, and then we get a little worse. So we see these two things, and we can also have a look at the standard deviation of this distance, and this becomes even more obvious. So here, most importantly, we can see that the effective distance median seems to be the most robust method. We did quite a large number of other simulations. As I said, we had a funny playground going on there. And to summarize the results, we could find that the effective distance median performs nearly as well as the backtracking method. When we did the analysis of the simulation result in a generalized additive model for location, scale, and shape, so just think of it as a zero-inflated Poisson model or zero-inflated gamma model. We didn't find any significant difference in the performance of both methods. We could see also in the previous slides that the performance decreases as the observation time progresses, which makes a lot of sense because the pattern gets more fuzzy and is kind of vanishing. In the model analysis, we could not find any considerable influence of the source node centrality. We were a little surprised by that, but then we could also confirm that in the application. The effective distance median is more robust in terms of detection performance, but is a little bit more sensitive to unusual network structures. So we tested unusual network structures like the Athens metro, which essentially gives you 4 stations in the city center where you can change the train, so a very centralized network, or the Göttingen bus network, which is also a very unusual network structure. No one uses the bus, by the way, in Göttingen. Everyone cycles. It's a little bit like Cambridge. And when we imposed background noise, we could still find both methods to find reliably the origin, but, well, of course, if you increase the background noise, it vanishes away, and that's what is expected. And testing different propagation mechanisms, both methods just did fine. And interestingly enough, we tried to improve the performance by introducing weighted networks with passengers, amount of passengers going on a link, or the number of trains passing on a link over the day. And we could only find a very slight increase in performance. So we could easily recommend both methods without weighting the network, so just using the essential information of the topology. Application. I like the applications most. So we got this example, which we have seen in the beginning of the spreading, and there was a damage report. It's very difficult to see. So there was a damage report at 6:25 in the morning. We cut off all the data which are happening overnight, because these are just usually caused by cargo, essentially. Funny things happening at night, but it really messes up your picture. And we can see the backtracking method in blue, and we can see on the y-axis the distance to the correct detection. So backtracking in the beginning does quite fine. After finds spontaneously pretty soon, like half an hour after the damage report, the actual origin, and then kind of stays in the area and estimates a station in the area, but then kind of vanishes away and detects or estimates a station 100 kilometers away. So it stays there. On the other hand, the effective distance median is a little bit slower in actually estimating the actual origin, but then stays there and says, okay, I'm pretty sure that this is the one. In comparison, the centrality-based method thinks first it's something 300 kilometers away, and then it's going even 700 kilometers away, which is essentially at the other end of Germany. You have an expansion of Germany from the far south to the far north. It's around 800 kilometers, I would guess. So, since we have the effective distance median kind of stacking at the actual origin, everyone would ask, okay, so we have this estimate, but how sure are you about it? Like, could be very sure, could be less sure. And you would expect the more data you obtain, the more certainty you get. So there's one idea of assessing that, and it's not a proper source uncertainty assessment. It's just an idea. So the idea here is to assess the second central moment of a source estimate by utilizing a type of subsampling. So every one of you, I believe, was thinking once during your time in network science doing subsampling, if you don't know what to do, you apply bootstrap, and then you realize, well, networks, dependencies, that's kind of difficult. So that's what we do here, and we just end up with something which is assessing it, but not really getting it. So for all the trains we observe, if we have individual train data, we do a subsample of the individual trains and their punctuality, so the delay magnitude. And then we aggregate the sampled information for each network node. Means so that we have like the standard observation snapshot picture again. We apply the source detection, source estimation method here, the effective distance median for visualization, and then we compare what is the estimation result by the subsample with the estimation result from which we get from all the data. And then simply we do that a number of times and calculate a proportion of estimate recovery, as we call it. The result looks like that for different subsampling proportions. We have the observation time on the x-axis and the proportion of estimate recovery on the y-axis. On the bottom, we see what the source estimate actually has been. So in the beginning, we estimate X105. That's a quite very central station in Germany, which is known to introduce a lot of disturbance into the system, as you would call it. And over here, we actually estimate the actual origin in X52. And we can see we kind of have an increase, but we kind of have a less steep increase before we find the actual origin, and then after that it actually goes really quickly up. and we get quite certain no matter what sampling proportion we use. We are totally aware that this sampling, that the proportion of estimated recovery is underestimating the actual uncertainty, because we do this subsampling. And but we are pretty confident in saying that at least you can do a comparison of how sure am I at 10 a.m. or am I any more sure at 3 p.m. So that would be at least a comparison over the course, the progress of the time series, and comparing the different estimates over time. Okay, I want to summarize. Backtracking and effective distance median show both good performance. That's what I believe, and that should be always the result of a paper. But they both have like strengths and weaknesses. And the nice thing is that they actually complement each other. So the effective distance median is a robust approach which reliably, at the time it actually finds the origin, identifies and sticks to it. On the other hand, backtracking is a very sensitive method which is really quickly, shortly after the damage report, finds the origin, but kind of hangs out in the area. So it doesn't say, okay, that's the origin, but somewhere in that area, in that region, there's the origin. But then it kind of has difficulties to settle on a particular spot, so it kind of goes away as soon a lot of, well, the spreading pattern processes. We believe we could show that we have a potential large amount of interdisciplinary applications of the effective distance median. On the other hand, backtracking is not that generalizable, we believe. So we tested backtracking on the foodborne disease outbreak of E. coli in 2011, and we couldn't estimate anything useful with it. So backtracking seems to work better if you have some cause which is continuously introducing disturbance into the system, since the algorithm is, well, essentially it kind of just looks for the local optimum or maximum of relative delay in the network, which could be like the global one, but usually it's a local one if you have noise in there. We are not, that's a usual limitation they tell us, but we are not limited to one source scenarios. We could also specify to be a multi-source estimation problem simply by applying community structure, community algorithms on it, and with that having certain subgraphs, and with that kind of reformulizing the multi-source problem into a number of single source problems. That procedure was introduced by Zhang et al. Limitations, there are still some, of course. So first thing I feel unhappy about is that I would like to have a proper uncertainty assessment. I'm working on that, that's another thing. The network resolution predefines the precision of your estimate. So it means you have a certain network and you will detect one particular node. You could also do that with edges or anything like that. But if you have a very regional network, you will have a larger precision, but also a larger uncertainty. So if you have a network of 300 nodes, you will be more likely to find it, but you're also less precise in where are you actually looking at. And then another part of my current project is to consider prior knowledge, because we usually know our black sheep in the system. So we know our stations who are known to introduce a lot of disturbance. And the other thing we were speaking a lot during this workshop about is to consider link uncertainty, because I like your I actually would like to quote that network not usually comes from the front door, but sometimes from the back door. So that's something I would like to consider. So I have an interesting diversity of funding going on for this publication. So most of the work has been done at the University of Göttingen, supported by a RTG for which was funded by the German Research Foundation. At the moment at Boston University, partly funded by the Alexander von Humboldt Foundation, and I'm very thankful to a very nice collaboration with the German railway operator, Deutsche Bahn, and Ingmar Schüle was very helpful in giving us insights what is actually needed in real life. So this is the references. The first one is the paper you hopefully can see very soon, and there's also a R package which is on Quran, and you're very welcome to test that out. And now I would be happy to answer your questions.
Okay. Any questions?
It's a very interesting topic, and as a German, I completely agree with your 5-minute delay annoys, especially if you have 3 or 4 changes that you need to do. But sometimes the delay isn't caused by a station, but by an edge.
Yeah.
So you made this remark that you could include multiple sources, but these would be interacting sources. Right? So could you just combine the two?
So there are 2 things I could think of to actually do the source estimation of an edge. So the edge would be a signal disturbance, which is a standard argument for why are we standing in the middle of nowhere. So that's usually happening on a track in between stations. So one thing would be an uncertainty assessment, that you actually find just 2 stations where the edge is in between, and you know, okay, that must be somewhere in between. That would be a simple version. Or you simply use a different way of defining your network. The way we used is one version, but there are like 3-4 other definitions of networks around in transportation science you could use, and one would be basically projecting on the edge and not on the station.
But you want to do both jointly, right? You want to get delays caused by stations as well as delays caused by...
Well, using bipartite network? Maybe? I would have to think it through, to be honest.
So there's dependence.
Yeah.
Okay, other questions? Maybe can I ask a question? So basically, you did subsampling in order to do come up with an estimation of uncertainty.
Yeah.
And clearly, the size of the subsample is important. So bootstraps, where you actually just take full repeat trains basically, and then re-estimate your your sources, will also give you an estimate of, or can give you an estimate of source, and therefore maybe some variation estimate. Why you're not doing something like that?
I did that.
Yes.
Was not successful. So I did play around with Bootstrap. I did play around with Jackknife. The problem is with bootstrapping, the method is too robust, so you don't get the variation in your bootstrapping samples, essentially. So here you get a 100% chance, which is not giving you any information. So I left out Bootstrap. That was like, okay, that doesn't work. So we need to do subsampling. Subsampling, I was playing around with Jackknife. Leave one out, doesn't work, it's not robust enough. Plus, if you compare to the theory of jackknifing the standard deviation of means, leave one out is fine. But if you go into a median, which is kind of the thing we are looking at, you need to leave D out. But then you go again into this maximize, you have to normalize your estimate, and then you end up with, first of all, what is your sampling scheme, what is your network dependency structure, and all that just didn't turn out right, and it was just not the right idea. And I decided to start over and use a different concept to do that.
Right. Other questions?
I didn't get if you consider also feedbacks in the propagation process. So the propagation process is only going to one direction, or you can have feedback loops?
You can have feedback loops, definitely. So just imagine you go up with a train, which people do weird stuff, right? So if you have a passenger transfer, and one person goes up but then wants to go down again, and you have to wait for this passenger transfer. And usually it would spread more in one direction, but essentially at one station you also have spreading into all other directions. So with that you also go back. And considering also that there are areas in Germany, yeah, believe it or not, but there's only one track for both directions. So you have the track occupation, which is even worse. So that's why one track connections are not very often, but they do still exist. But that's usually personal experience, usually for regional trains, to be honest. So yeah, so, any direction is possible, also going back.
Okay, last question.
So for the your previous application with the E. coli outbreak, to what extent does it make, if you know, to say the evolutionary history, or like not necessarily the transmission tree, but the sort of, I mean, the evolutionary, in a lot of those outbreaks, you can reconstruct the evolutionary history of all of your strains that you sampled. Does that do you know if that improves your chances of getting the source right, and to what extent is?
Do I understand correctly that you're referring to evolutionary history of the pathogen itself?
Yes, yeah. Or even the transmission tree.
I'm not 100% sure, but there were attempts, and I'm not sure whether they were successful or not, to actually combine that, because you have like the network of the genetic variation, essentially, and then you have the network of the transmission tree, and to combine that, there's some thinking necessary. But to be honest, I'm not very sure what the current stage is of what these people do. I would have definitely to
in the
look
cholera
at that.
case in Germany it doesn't work, but in other cases like cholera it's working, like in Haiti outbreak. Yes, they found out.
The problem with the E. coli was that they actually came out and were like, oh, what's that? E. coli was usually transmitted just in between kids. Usual for foodborne disease in industrialized countries. But here we had an unusual serotype, so people were like, we never really have seen that before. That made it in particular difficult to actually predict where it is going to, where it comes from, what might be the transmission vehicle, why are so many people dying of it, why is the severe version of E. coli, the whose version is so prominent and has such a high prevalence. So that all that part was really puzzling a lot, just by having a new serotype which came, I don't know, I'm not infectious diseases that much, but which came pretty much out of the blue.
Okay, well, I would say let's thank Juliane again. Right. Now is the switch off computer first.